In this video, we are going to give more example about Euler and Hamilton circuit, and we will also take more example about finding the shortest path in a graph. So first, let us review the definition of Hamilton path and circuit and some of the conditions we need to consider to find whether a graph has a Hamilton path or circuit. A Hamilton path of a graph or digraph is a path that contains each vertex exactly once, except that the end vertices may be the same. A Hamilton circuit or cycle is a Hamilton path that is a cycle. Contrast to this with an Euler circuit which contains each edge exactly once. Now we are trying to review those concepts and we link them to the traveling salesperson problem. Figure 1 shows graphs with Hamilton path but not Hamilton circuit. As you can see from the figure, we have a Hamilton path in both graphs, but we cannot end up in the same vertex in both graphs. Two vertices V and W of a graph G are adjacent if there is an edge E, which is basically V and W joining them. The vertices V and W are the incident with such an edge E. Also E is incident on V and W. Two distinct edges E and F are adjacent if they have a vertex in common, as you can see from the figure. Back again to the traveling salesperson problem. To visit every vertex of a graph G only once by a simple cycle. Such a cycle is called a Hamilton circuit. If a connected graph G has a Hamilton cycle, G is called a Hamiltonian graph. A Hamilton cycle or path in G will be a subgraph of G. Enough edges, then G has a Hamilton circuit. Add a red edge between them as shown in the figure. In this graph, the number of vertices is 7. The degree of B plus the degree of C greater than or equal n minus 1. If G has a Hamilton circuit, then the degree of V greater than or equal 2 for all V on graph G. If the degree of V equal 2, then both edges incident on V are in Hamilton circuit. If the degree of V greater than 2 and two of the edges incident on V are in a Hamilton circuit, then the other edges incident on V are not in that Hamilton circuit. A complete digraph where V, the number of vertices, is greater than 2 has a Hamilton path. Now recall Euler circuits. Graph G has a Euler circuit if and only if every vertex of G has even degree. And this is basically the necessary condition. If G has an Euler circuit, then every vertex of G has even degree. The sufficient condition that if every vertex of G has an even degree, then G has an Euler circuit. Establishing whether or not a graph has a Hamilton circuit is non-trivial, no elegant. The characterization of a Hamilton circuit exists. Although several necessary or sufficient conditions are known, sufficient conditions usually require enough edges. Dirac's and Euler's theorem provide sufficient conditions for Hamilton circuit, but not as necessarily conditions for satisfying that the graph has a Hamilton circuit. In a graph G, two vertices are adjacent if they are joined by an edge. If each vertex of a connected simple graph with n vertices where n greater than 3 is adjacent to at least n divided by 2 vertices, then the graph has a Hamilton circuit. And this is basically Dirac's theorem we discussed before. So consider the graph shown in figure 3 where n equals 7. Now n divided by 2 equals 3.5. Since each vertex is adjacent to at least 4 other vertices, the graph has a Hamilton circuit by Dirac's theorem. Dirac's theorem gives no information about being non-Hamiltonian it does not tell us how to find a Hamilton circuit. Find a Hamilton circuit in the graph G shown in figure 4. Now in this case, we will try to find two Hamilton circuits in this graph. So first, let us start by going from D to A, then to E, then to B, then to G, and then we go to C, then to H, and then to J, and then to F, and then to I, and then we go back to D. So this is the first circuit we find in the graph. Can we find another Hamilton circuit in the same graph? Yes, we can. So first we go from A to B, and now note that while vertices A and B were one previous Hamilton circuit, the edges A and B was not. So the vertices were involved, but the edge between them was not involved in the previous circuits. So we go from A to B, and then to C, and then to G, and then to H, and then to J, and then to F, and then to E, and then to I, and then we go back to D, and finally we land at A. Now in this figure we have both solutions displayed so you can have a comparison between them, so you understand what is the difference between the two Hamilton circuits in this graph. Now let us make a link between the use of Hamilton circuits to solve the traveling salesperson problem for the graph shown in figure 5. By finding the total weight of all Hamilton circuits and determining a circuit with minimum total weight. First, we make a table similar to table 1 shown in the slide. Thus, we see that the circuits A, B, E, C, D, and A, and the circuit A, B, E, D, C, A, or the same circuit starting at some other point but traversing the vertices in the same or exactly opposite order, are the ones with minimum total weight. I wish you have understand both Hamilton circuits and traveling salesperson problem after watching this video. Thank you for watching and see you in the next one.